Hello physics students, this is part 2 of chapter 10, still looking at potential, still looking at energy and work and how all that provides a big paradigm, big picture for physics. So this slide 49 in this PowerPoint, talks about friction. Friction has to do, in this big equation, where you got all the initial energies equaling all of the final energies. This delta ETH, just to remind us, how do we arrive at, what is that? That's the change in, that is the change in thermal energy. All right. So we've talked about this already, but just to remind us, in your equation, Ki plus Ui, we could say plus ETHI equals Kf plus UF plus ETHF. And if we take this term and move it over here so that it's subtracted, so minus ETHI, then this right here, final thermal energy minus initial thermal energy, is just written as this delta ETH, or change in thermal energy. So this is not any different than the way we've always written it. It's just rearranged a little bit. So the ETH has to do with friction. And that change in thermal energy equals the force of friction times the distance that friction force applies to the system. Which that makes sense, because that's what work is. Work is force times distance. So this is the work done by friction. And the work done by friction equals the change in thermal energy in the system. Work and energy are essentially the same thing. All right. So the mechanical energy being kinetic and potential energy, those things, it says, that are not conserved if there is friction. They're not. They say it's not conserved because the initial does not equal side of the equation does not equal the final side of the equation in the way that it's written in this case. But you could still consider all of the energy together being conserved if you consider the thermal energy to also be part of the system. However, here it's considering the work done by friction to be an external work done onto the system. So again, it just depends on how you define that system. So if we go with what they're saying here, this is external to the system, then it is right that the mechanical energy is not conserved, and we might consider this to be a non-isolated system. Because the thermal energy, the change in thermal energy, is greater than zero, because friction always makes surfaces hotter, never cooler, the final mechanical energy is less than the initial kinetic energy. Should say the final mechanical energy is less than the initial mechanical energy. So I think that's a misprint. I'm going to go ahead and change that. Alright, some fraction of the initial kinetic and potential energy is transformed into thermal energy during the motion. Quick check 10-4. A child is on a playground swing, motionless at the highest point of his arc. What energy transformation takes place as he swings back down to the lowest point of his motion? Alright, so when he's at the highest point of his motion, we might even draw a picture of it. Here's the child, and there's the pivot point of the swing. He's swinging down to the lowest point of his motion. He's going, and he's still for a minute right here. So there's no kinetic energy. It's all potential. as the potential energy then, as he starts to move, the potential energy is converting into kinetic energy because there's a velocity. And down here is where he's actually going the maximum velocity at the bottom. And then it's also all kinetic energy here. And then it starts to change back into potential energy as it continues to go up. So does it tell us anything about friction? It doesn't tell us anything about friction, really. So I think the answer is this: potential is changing to kinetic, but it's actually changing probably to kinetic, and if there's any friction at all, if we consider that at all. So it's also changing to delta ETH. But maybe it's not wanting us to consider that, but I think I'm going to choose choice B, and it is choice B. A skier is gliding down a gentle slope at a constant speed. What energy transformation is taking place? All right. So the skier is skiing down a slope. That means it's potential energy changing to something because it's going down a slope. Its height is changing. Its position relative to gravity is changing. What's it changing to? Well, you might think, well, it's changing to kinetic energy, but it's skiing at a constant speed. So the kinetic energy is not changing. So then if that's the case, the only thing it could be changing to is ETH. So I think we're going to choose choice D. And that is correct. So it's the friction, the little bit of friction between the skis and the snow, and that's usually going to be melting a little bit of that snow. All right. We also need to discuss a different kind of potential energy, elastic potential energy. So this figure shows a spring exerting a force on a block while the block moves on a frictionless horizontal surface. Let's define the system to be block, spring, and wall. So the system is the wall, the spring, and the block, the whole thing. The spring is in the interaction between the block. The spring is the interaction between the block and the wall. Because the interaction is inside the system, it has an interaction energy, the elastic potential energy given by. So this is the formula for elastic potential energy. And it looks a lot like the formula for kinetic energy. Kinetic energy is 1/2 mv squared. So this is similar. The 1/2 is still there. The mass is an intrinsic property of the object that has the kinetic energy. K is an intrinsic property of the spring. It's actually the stiffness or the rigidity of the spring. If it's a big thick spring versus a little thin slinky type spring, that will change the value of K. And then delta S is the distance that the spring is compressed or stretched. And all that formula together. So notice that the distance of stretch is a more influential term in this formula because it's a squared term, a quadratic term we might call it, than the rigidity of the spring, which is just a linear term. Quick check 10.6. A spring-loaded gun shoots a plastic ball with a launch speed of 2 meters per second. If the spring is compressed twice as far, the ball's launch speed will be what? Well, remember the potential energy the elastic potential energy for spring is 1/2 K delta S squared. So if we change this term, whatever we change it by, changes by a factor of the square of that change. So if it doubles, then this whole thing is the double part's going to get squared, so it's going to be quadrupled. So this is going to be times 4. And if that all turns into turns into kinetic energy, then it's going to have four times the kinetic energy that it had in the first instance. So I think the answer that the kinetic energy, is energy that has velocity. I think the velocity will be 4 times the original velocity. 4 times 2. Light speed of 2 meters per second. All right, let me analyze this. Let me analyze this a little bit more thoroughly. So this all changed to kinetic energy. So that first kinetic energy is going to be 1/2 times m, and the original speed was 2, so 2 squared. And we're going to multiply, and we're going to have 4 times what that was, becoming the kinetic energy in the second instance. 1/2 m and this v squared that we don't know. So that being the case, and we want to know what v is in the second instance. The 1/2s cancel out, the m's cancel out. So this is a 4, this is a 4. 4 times 4 is 16, equals v squared, square root both sides, and v would equal 4. So I think the correct choice is actually D. And it is. That was a little confusing. All right, tick 10.7. A spring-loaded gun shoots plastic ball with a launch speed of 2 meters per second. If the spring is replaced with a new spring having twice the spring constant, but still compressed the same distance, the ball's launch speed will be what? Okay, so potential energy of a spring is 1/2 K delta S squared. And that all is going to be, we're going to double K. So if we double K, that's going to multiply this whole thing by a 2, just a linear 2. So the original spring potential energy turns all to kinetic energy, right? Turns all to kinetic energy. And kinetic energy is 1/2 m and 2 squared. But we're gonna double that because we're doubling K. The question is, what is the new velocity if we double the energy by doubling K? 1/2 m v squared. Again, the 1/2s can cancel, the m's can cancel. So this is going to be 4. So 2 times 4 is 8. 8 equals v squared. Square root both sides. And the square root of 8 I would probably guess to be choice C. So I think the answer is C. 2.8. And that is correct. Okay. For a system that has gravitational interactions, elastic interactions, and friction, but no external forces that do work, the energy principle is this. This is looking a bit more complex as we have more and more energies to keep track of, but the message is both simple and profound. For a system that has no other interactions with its environment, the total energy of the system does not change. It can be transformed in many ways by the interactions, but the total does not change. And I think if we, as I've told many of you, apply that to the universe, and what does that tell us? It tells us that the universe itself is not a closed system. And its existence, in the beginning of its existence, when there was no matter and motion, and now there is, that means that there must be something outside of the universe that has done an external work on the universe to change that energy from being 0 to something greater than 0. And if you define the universe to be all physical things, all material, physical stuff, then what does that tell you? That means there's something outside of that definition. And I'll leave it at that. So that gives us the law of conservation of energy. And here that is. The total energy of an isolated system is constant. The kinetic potential thermal energy within the system can be transformed into each other, but their sum cannot change. Further, the mechanical energy is conserved if the system is both isolated and non-dissipative, meaning it doesn't have any dissipative forces in it like friction. All right. Basic energy model. When a system is isolated, the energy of the system, the total energy of the system is constant. So you have these energies that are transforming into each other, but there's no energy flowing into and out of the system. The total change in the energy of the system is zero. Okay, here's a problem-solving strategy you might want to check out. And here's a problem. The speed of a pendulum. A pendulum is created by attaching one end of a 78 centimeter long string to the ceiling and tying a 150 gram steel ball to the other end. The ball is pulled back until the string is 60 degrees from vertical, then released. What is the speed of the ball at its lowest point? All right. I'm going to move this out of the way to do some work for a second. I don't think I can move it out of the way. Maybe I can make it small. Then I'll change that. Yeah, that's fine. All right. 78 centimeter long string. Is pulled back so that it makes a 60-degree angle. Didn't it say with the vertical? Let me make sure. From vertical. And 150 gram steel ball. So we got ourselves a 60-degree angle from the vertical. And this is a 0.15 kilogram ball. All right, so as this thing swings, we could do this many ways. I mean, you could do force, diagram, sum of the forces kind of thing, free body diagram, kinematics, all that good stuff. But this is where, if you analyze this with the work and energy theorem, then it's going to make life pretty easy. There's no little trig here. So what is making this ball swing when it's let go? The force of gravity. The force of gravity is what is doing work on this system. So the force of gravity is doing the work on the system. So it's changing potential energy to kinetic energy. So what is that initial potential energy? Potential energy due to gravity is mass times acceleration due to gravity. So that's basically the force of gravity right there, times delta H. Again, this is the work done. You can say this is the work done by gravity. Also, force times distance. All right, so the delta H is what we want to consider. So the delta H is what is the difference in height from here to here. So what is this difference in height? That's going to help us to figure out the problem. So I'm going to use some trig. I want to figure out this length, and if I then figure out this length, then subtract them, and I'll know delta H. All right, and I actually already know this length. This length is 78 centimeters, 0.78 meters. So just figure out this length, and we'll be good to go. All right, so this is a 30-degree angle. The hypotenuse, we know the hypotenuse. This is the opposite side from that. So let's just call this x that I'm solving for here. So x over 0.78 equals sine 30. So x equals 0.78 times sine 30. And if I can do that in my calculator, it's 0.39. Should have known that because I should remember the sine of 30 is a half. All right. So then, if this is 0.39, and this is 0.78, then this change in height here will be the difference. 0.78 minus 0.39 is 0.39. So this potential energy is 0.15 times 9.8 times 0.39. And that is 0.5733. And so if we take our energy principle equation thing and apply that to this problem, what do we have? I'm going to be very thorough here. I'm going to say U initial plus K initial equals U final plus K final plus delta ETH plus work, the external work done on the system, but this is 0. There's no external work done on the system. And ETH is also 0 because there's really not friction to speak of that we need to consider. The heat of the system is not changing. So there we go. So let's just consider this to be where we're letting it go there. So the kinetic energy at the beginning is 0, and when it gets to the bottom, we can say the potential energy there is 0. So now it's just potential energy at the beginning equals the kinetic energy at the end. U initial equals K final, and so U initial 0.5733 equals 1/2 mv squared, so 1/2 times 0.15 times v squared, and we just do a little algebra. 0.5733 times 2 to get rid of the 1/2, divided by 0.15, and I get 7.644. Then square root that, and I get V equals 2.76. And that should be the answer if I'm remembering correctly what this problem is asking for. What is the speed of the ball at lowest point? Yep, that's the answer. And that is what the PowerPoint has as well. Quick check 10.8. 3 balls are thrown from a cliff with the same speed, but at different angles. Which ball has the greatest speed just before it hits the ground? Ooh. We could do some kinematic stuff on this, but using the energy theorem, what if we start here They're thrown with the same speed. So their initial kinetic energy is going to be the same regardless. And their initial potential energy is going to be the same regardless. And if the final energy at the ground is 0, so this equals the final kinetic energy, and this is the same in each instance. Therefore, the final kinetic energy is also the same in each instance. They all have the same speed at the end. So whether you chunk the ball down with a velocity, or chunk the ball up with the same velocity, or chunk the ball out with the same velocity, when it hits the ground, it's going to be going the same overall speed when it hits the ground. Pretty neat. Quick check 10.9. A hockey puck sliding on smooth ice at 4 meters per second comes to a 1 meter high hill. Will it make it to the top of the hill? So initially this thing has kinetic energy. And I'm going to take some shortcuts now because you've seen the thorough way. Initially it's all kinetic. So kinetic, initial, and let's just say when it gets to the top of the hill, we just want to know, does it have enough energy to get to the top of the hill at all? So we could say at the top of the hill, it could even be going 0 meters per second. So have no kinetic energy at the top. We just want to see if it'll make it at all. It may make it and then some. But if it just barely made it, that's the case we're trying to figure it out. So that equals the final potential energy, because there's no kinetic energy at the end if it just barely makes it. So 1/2. Does it give me the mass of the hockey puck? No, it doesn't. So just leave it as m times 4 squared equals m g, so 9.8, delta h, which is 1 meter in this case. Notice the m's cancel. So we got 4 squared is 16 times 1/2 is 8. And over here we got 9.8. So the final potential energy would be greater than the initial kinetic energy. So that means that the puck won't make it. It would have to have a greater initial kinetic energy to climb that hill to reach that final potential energy at the top. So it will not make it. No. All right. I think I'm going to stop it right there and call this part 2 of chapter 10.